In this video, we're going to look at Gauss-Jordan elimination, and we'll first do a quick example. We want to know whether the matrix below is in RREF, in other words, whether it's in reduced row echelon form. Well, to answer that question, let's circle the leading entries in each row of the matrix. In the first row, the first non-zero entry that we run into is this one. In the second row, the first non-zero entry is this guy, and the bottom row is entirely zero, so there's nothing to circle in that bottom row. Now, in order for a matrix to be in RREF, four properties have to be true. Any zero rows have to be located at the bottom of the matrix. Each of the leading entries have to be 1. These leading entries have to be moving down and to the right. And the leading entries have to have zeros in the rest of their columns. So what we're seeing is a problem with this entry here. This -1 here would have to be a 0 in order for this matrix to be in RREF, and that is the only problem with this matrix. So the answer is no. And just as a follow-up comment, I'll say if that had been a 0, if we had 102 and then 0, 1, 3, 0, 0, 0, then the answer would be yes. This matrix here would be in reduced row echelon form. So we'd like to solve the following system using Gauss-Jordan elimination. Let's set up the augmented matrix for our system. So we can label our columns with our variables here. Vertical bar represents the equal signs, and over on the right we'll have the constants. So that top equation translates into 3, 4, 2, 24. 3x plus 4y plus 2z equals 24. And similarly, we can copy in the coefficients from the next two equations. So I like to just double check my copying as I go. Okay, and that looks good. Now our goal, if we're doing Gauss-Jordan elimination, is to get this augmented matrix into reduced row echelon form. Remember, if you're doing Gaussian elimination, you only have to go to REF. But if you're doing Gauss-Jordan elimination, then you have to take this matrix all the way into the reduced REF, the reduced row echelon form. So let's apply our elementary row operations. The first thing we want to do is get a 1 in the upper left-hand corner here. So there are a few options for how to do that. We could divide the top row by 3, but that would create some fractions here. Probably a lot easier just to swap the top two rows. So let's swap row 1 and row 2. And we'll leave the bottom row the same. And again, probably a good idea just to double check your work as you go. So there we go. Now I like to circle this 1. I usually refer to that as the pivot. And we're going to use this pivot now to eliminate the 3 and the 5 below it, because we need to get zeros in the rest of this first column here. So what we'll have to do to get rid of the 3, we'll take row 2 minus 3 times row 1. Okay, in order to eliminate a number, you're always taking the row that you're on, plus or minus an appropriate multiple of your pivot row. So 3 minus 3 times row 1 would work here. For the bottom row, to get rid of the 5, we'd have to take row 3 minus 5 times row 1. Alright, so the row that you're on plus or minus an appropriate multiple of your pivot row. If it's a 5 that you're trying to eliminate, minus 5 times your pivot row will eliminate that 5. Alright, so let's figure out our entries here. We're just recopying that top row that is not changing. and we'll go row 2 minus 3 row 1. That gives us 0, negative 11, positive 20, and minus 21. And for the bottom row, row 3 minus 5 row 1 is going to give us 0, minus 11, positive 20, and minus 21. Okay, and we can just double check that work here before we go on to the next step. So that looks good. All right, next thing we will do is from our current pivot, we're going to move down to the right. So we're going to move over to this negative 11, and we'd like that to be our next pivot. So we are going to take row 2, and we're going to divide it through by negative 11 to create a 1 in that position. So that will give us a 0, 1, a minus 20 over 11. We have to be very careful about our signs here when we're dividing through by negative number. Over on the right side, positive 21 over 11. And I'll just recopy the top and bottom rows because those are not going to be changing. So I've just recopied this matrix from our previous step, and we had created this pivot of 1 here in the second column. So the next thing we need to do is get rid of the other numbers, the other entries sitting in that second column. We need to get rid of this 5 and this negative 11. So let's go, giving ourselves a little bit more room here. Let's go row 1 minus 5 times row 2. Okay, we're doing the row that we're on plus or minus an appropriate multiple of our pivot row. If it's a 5 that we're trying to eliminate, then minus 5 would be an appropriate multiple. And for the bottom row, we'll go row 3 plus 11 times row 2. All right, so working on the top row. Row 1 minus 5 row 2 is going to give us 1, 0. Now we're going to have to do a little bit of algebra down below. So we're going to take negative 6, and we're going to subtract off 5 times this fraction here. So I'm going to make that plus 100 over 11, and creating a common denominator, that's negative 66 over 11 plus 100 over 11 gives us 34 over 11. All right, so that gives us that entry there. We've also got to do 15 minus 5 times 21 over 11. So I'm going to say 15 minus 105 over 11. Creating a common denominator gives us 165 over 11 minus 105 over 11, which is 60 over 11. All right, so this sort of arithmetic, you can do it as quickly or as slowly as you like. Typically, that's about the amount of work that I like to do down below. The middle row can be recopied. So 0, 1, minus 20 over 11, and 21 over 11. And then for our bottom row, we're going to go row 3 plus 11 times row 2. All right, so we're getting 0, 0, 0, and 0. Now at this point we can check that our matrix is in reduced row echelon form. It's just a matter of circling the first non-zero entry in each row. So there are our leading entries, and we'll just check the 4 properties here. So the leading entries are all 1s. They are moving down and to the right. They do have zeros in the rest of their columns, and any 0 rows are located at the bottom of the matrix. So yes, all 4 properties are satisfied. That tells us that we're ready to then solve this system. So we might want to just relabel our columns here. Remember, the columns represent our variables x, y, and z, and then finally our numbers over on the right side. And what we're interested in here is particularly any column without a leading entry in it. So notice that the column for Z does not have a leading entry. That means that we need to give Z a parameter. So that's the first step to our solution here, is just to say Z equals T. Okay, the rule is that any column without a leading entry gets its own parameter. And then we can use this parameter here to solve for the values of x and y. So let's take a look at the top equation. That says that x plus 34 over 11z is equal to 60 over 11. If we solve for x is equal to 60 over 11 minus 34 over 11 times z. And now we're effectively plugging in that previous value of z. Rather than calling it z, we're going to call it t to represent that it's free to take on any real number value. So we should say x is equal to 60 over 11 minus 34 over 11 times t. All right, so there's our value of x. And looking at the second row of this matrix here, y minus 20 over 11 z is equal to 21 over 11. And if we solve for y is equal to 21 over 11 plus 20 over 11 times z. And again, we're plugging in our previously known value of z, which is t. So y is equal to 21 elevenths plus 20 elevenths times t. So let's write up our answer in vector form. xyz is going to equal the constant part of each variable plus t times this vector here, which represents our coefficients of t. So filling in the coefficients, x is equal to 60 over 11 plus t times negative 34 over 11. Y is equal to 21 over 11 plus 20 over 11 times t. And z is equal to, well, the constant part is 0, 0 plus t times 1. So there we have our solution in vector form.